So as mentioned, I am affiliated with 2 places, but the work that I will present is mainly has been done over the past 3 or 4 years at KAUST in Saudi Arabia. So this is the last presentation, and I have to say I'm honored for this and humbled. At the same time, I will try to be as entertaining as possible and not to bore you with lengthy derivations, not to underestimate the derivations. It's just I'm not as good as many of the people are here. So I'm going to emphasize the theme of the symposium, which is exploiting nonlinear dynamics for applications. And hopefully this is the message that I will get out of this. Now, finally, the applications that I'm going to talk about, these are not devices that are ready to be commercialized. So I'm just going to hint for devices that, if someone carries and continue research in these, they might be materialized into commercial devices, or they might not be. So I have to be careful that what I'm going to talk about are far away from being mature devices. Nevertheless, hopefully this will inspire discussion and research in the field. So this is simply the outline. It's going to be introductory remarks, and then kind of 2 categories of devices where dynamics is evident, something called smart sensing and actuation, or switches. And then I'm going to talk about a category of devices, shallow arches, and talk about some of their nonlinear behaviors, and then touch on some of the potential applications. And then I'm going to conclude. So let's talk about some introductory remarks. So what you see in the slide are some micro and nano systems. And what is special about these small-scale systems that they are compliant. And they are, in general, thin structures compared to their other aspects or other geometrical features. So these are not bridges or buildings that undergo small motion. These are naturally actuated to undergo large motion. And hence, geometric nonlinearities, material nonlinearities, other nonlinearities are usually very significant. The other aspect of these are multi-physics devices, meaning you need to actuate them with electrostatic force, electrothermal, and they are subjected to nonlinear damping. So this is what we call multi-physics fields. So they are rich, they are intriguing from a physical point of view. So the state of the art is what you see. This is an emerging field, has been emerging for the past, I guess, 20 plus years, but especially at the nanoscale, it's getting more momentum just because the issues of nonlinearities are more significant. And this is a bunch of randomly selected publications over the past few years. You see keywords like parametric excitation, synchronization, bifurcations, period doubling, stuff that we are familiar with and we know very well in this community. Unfortunately, this community of researchers, and most of the time, they don't recognize our existence. And hence, rarely you see some of our beautiful theoretical work that we feature in this conference and others mentioned anywhere. And I don't know which mistake is it, our community that we don't reach out, or them, they don't reach out, but something definitely is wrong here. I have to just to pay a little tribute for my advisor, who is usually among the few people who are mentioned and recognized, as you can see here. Usually his books, whether these or the book with Balachandran, are usually cited, but not much beyond. So at least, the legacy of Professor Naife is still continuing and continues. The current state of the art for these micro and nano systems, they are already used in our cell phones and our automobile cars and so on. However, because there is always demand to reduce power, to boost sensitivity, to realize smarter functionalities, they continue to be under heavy research so that you achieve essentially more of everything. These devices, they of course are opportunities to do both fundamental research for reasons that I will explain, and also practical research. However, they also bring a big package of challenges. Some of them I already mentioned. They are multi-physics and they are strongly nonlinear. In fact, in many cases, I cannot apply perturbation approximations just because of the strength of nonlinearities. Also, and hence you can see this is a carbon nanotube, was featured more than a decade and a half ago now. And you can see lots of frequencies that they cross sometimes and they get close to each other. And at that point, people did not have clear understanding of what they are dealing with. So there was a clear call for thorough fundamental and theoretical study of such systems. Finally, I have to mention that these are noisy systems in which the noise level is sometimes extremely high, and to just exceed the noise level and see a measurable signal, or to get a signal to noise ratio that is reasonable, sometimes you exceed the linear regime and you find yourself in the nonlinear regime. So these are just general remarks to keep in your mind. My objective today is to, usually this is a message especially to the outside community, outside this, that it pays to develop a proper modeling techniques to study micro and nano systems, and it's worth it. So we do this math and complexity, and my argument that you will get an understanding that will allow you to realize devices that you cannot realize trivially or using linear modeling techniques. So I guess this is the main message out of this presentation. So a little bit of background, since many of us are outside the micro or MEMS area. So for example, one of the features of MEMS, they rely on electrostatic forces. And this force is nonlinear. It kind of goes like 1 over the distance square between the structure and a lower electrode. And as you can see in this law, so it does not goes like W square or W cube, it's like 1 over W square, something like that. And if we add some voltage load into this structure, then what happens, there will be attractive forces between the structure and the lower electrode. So the structure will be deflected if it's compliant. And if we plot the potential function of the structure, then you will see kind of a single well potential, like what you see in the diagram, with a possibility to escape under some kinetic energy. Now, if you keep, this is external source, so in theory I can reach infinity if I want, but the structure will not be able to resist all of this force. So there is a threshold of instability at which case the structure will collapse and go down. And in this case, of course, the potential will lost its well and you have an escape. So this is what they call in the literature as pull-in. It's kind of like the buckling instability threshold where you have a frequency of 0 or an eigenvalue of 0. All right, let's take a look and add, in addition to the DC bias, an AC harmonic load. So you have a clamped beam and you are biasing it with some force and then you are vibrating it. So what would be the expected response? So to simplify it, let's start by putting this DC bias to be as small as possible. In this case, it's just a clamped beam. If you excite it with large motion, then there will be mid-plane stretching and hardening nonlinearity. So experimentally, this is what you get. You get hardening behavior. This is expected. Now, what happens when you increase the electrostatic force, or VDC? Well, the electrostatic force, I have to mention, they are quadratic in nature, inherently quadratic in nature. And hence, there will be a softening effect that will kick in as you increase this VDC bias. And at some point, actually, it will cancel out the mid-plane stretching. So this is experimental data showing almost a linear curve as I increase VDC. Now, as you would expect, increasing the load even more, you will get a softening effect. So this is hardening, linear softening transition. So this is enough background. Let me talk about some ideas and devices. So the first idea, it will sound trivial. It's trivial. I just want to make use of these jumps to realize a sensor. So when a jump occurs, something will happen. So I will start with gas sensing. It's really what you have. You have a structure in which you can coat it with polymer. In this case, it's what they call HCAST or MOF, metal organic framework. But what it is, it's a structure that is spongy, so it can absorb gases and stuff like that. So after fabricating and so on, we will have this setup, which is an optical setup, in which we have an environmental chamber. I will have the structure inside. I'm going to expose it to some gases with some flow controller so that I control the flow of the gas inside. And then I will watch the motion using laser Doppler vibrometers optically. Okay, classically, if you have a structure and you load it with some mass, then what happens, the mass of the structure will increase. So there will be a shift in its resonance frequency or natural frequency. K over M becomes K over M plus delta M. And classically, that shift in frequency is proportional to the amount of added mass. So this is, in a linear sense, how these structures are used as mass detectors or gas detectors. Now let's take a look and let's excite the structure into the nonlinear regime. So what happens in this case, you can get a softening or hardening behavior depending on the nonlinearities. And the idea, instead of chasing this resonance peak, I'm gonna fix my excitation frequency and kind of record the amplitude of motion. So you can think about this dashed line as the operating frequency, right? So what happens when you expose the structure to mass, then this curve will shift backwards. And if the line is constant, then you can imagine the amplitude will increase. Or to make it simple to our imagination, just imagine we are climbing this curve when we expose the structure to mass. So that if I'm watching the amplitude, I'm gonna see the amplitude of motion growing, and then at some point, there will be a jump. So the idea that, well, when the amplitude grows, this means you are absorbing more mass. And hence, at certain threshold, there will be a jump phenomenon from higher branch to lower branch. And maybe this can indicate that the amount of sniffed mass or concentration of gas exceeded certain safety threshold. Then you can program this jump and make it an indication that you exceeded, the safe threshold and, does an action. So you can think about it as a switch triggered by the action of mass. But for that, I need an algorithm and a microcontroller, of course, because I need to always watch for the amplitude and record the sudden change in amplitude between this point and this point. So essentially, this is what we did in this part of the research, and this is jump down switch, and this is jump up switch. With the use of a microcontroller and an algorithm, you can watch the drop of the amplitude, and then you can have a LED or something to indicate that the amount of caught mass exceeded certain threshold. This is fine, but also the fact that I need a microcontroller and an algorithm is bothering. So can we do it without an algorithm or a microcontroller? The answer is yes, but I have to dig deeper into the dynamics. So for that, let me go back to this Helmholtz oscillator with a quadratic nonlinearity. And this is a sketch from Thompson and Stewart, classic for people who know the field. And what you have, if you have this spring mass number system, then you can characterize the kind of bifurcation the system will experience as a function of the frequency and the forcing. So in this map, for example, for a forcing below this line, then the system is linear. There is nothing strange. Above this line, then you start to have hysteresis and softening or hardening. And then as we climb up, what happens, the basin of attraction for the system becomes weaker. Still, it's multi-stable and it has jumps, and actually it can jump out of the well to the infinity in this case, or it may not, depending on the initial conditions. But once you reach this V shape, then you have a must or inevitable escape band in which this oscillator cannot oscillate, and essentially the ball will escape the well, or if you think about MEMS, the structure will collapse. Okay, so experimentally, what happens if I excite my system with large harmonic force? Then this is what you will see. You will see these gaps in the frequency response curves. So this is one, increase the forcing, this is another. So these, kind of resemble what you see there. Actually, I can put these on a map like this one, and this is what you get. You get this V shape where you have VAC, which is the forcing, and the frequency. And within this band, the structure, there is no hope for the structure to vibrate. It must collapse, right? I just want to warn you that what we see here is not the same V as we see here, because experimentally, there are noises, there are disturbances. The system is not going to wait quietly until it reaches where theoretically the solution disappears. So chances are I am pulling in somewhere before. So actually, this is schematic showing if I observe the basin of attraction, how it erodes for the system. Then, of course, it's healthy somewhere here. It keeps eroding until you get zero basin of attraction. And I had the chance to work over the years with Stefano and Laura Rizzucchini. And we were looking into this basin of attraction, how it erodes as I sweep the frequency and forcing. And we were comparing it with the experimental data of instability. So this is a busy diagram, but if you focus into these discrete points, these are the experimental data. And what you see here, you see 40% and almost also 30 to 40%. So the message here that this basin of attraction, if it erodes and it becomes 40%, for example, of the original healthy one, then practically I must pull in, I must collapse. So for people who may be unfamiliar, I'm sure most people familiar, white means here unstable and black, or opposite actually, white stable and black unstable or collapse. So the bottom line, this is predictable, it's not bad. We can predict this. We can predict this, and the predictions of experiments and theory, they match. All right, so back to this idea of a switch triggered by mass. So the idea here by animation is easy. I want to realize this opening in the frequency response curve where I have instability. I want to stand up at a distance where I have a stable oscillation. I want to expose the structure to mass, and then what happens? This will shift backward the frequency response curve such that the operating point now is inside the instability regime. And then what happens? This structure becomes from a vibrating structure into a collapsed structure. With a proper circuit, you can get this collapsed structure to close a circuit. So you have a switch, an electrical switch now, but it's triggered only when the amount of mass exceeds the desirable threshold, which is determined by the operating point. So I guess this is the idea, and this is the experimental realization of this idea. So this is the frequency response curve obtained experimentally. So this is the operating point, and it's first we test that the response of the system is stable, because you have noise, and actually if you are close here, you might pull in or go to the instability. So this is stable, as you can see. Now I'm going to expose the structure to vapor, and then you see how the displacement will grow, and then eventually it will collapse like a switch at this region. All right, so let's add more function. We are dynamics people, so I guess we can do better than this even. So one idea, let's look into multimodal excitation. So in this sensing literature, what they are concerned of usually is the temperature influence into the mass. Essentially, if you have a clamped beam and the beam, is heated, then of course it will get an axial force. It will translate into shift in the frequency, which can be mistaken for a mass. So how you compensate for temperature effect? Well, the approach in the literature, you build two identical systems. One you expose it to mass, the other one you don't expose it to mass, and then you subtract the response of one from the other, so that if there is temperature effect, it will be canceled out, right? So all what we are doing here is to say, well, let's have the same structure, but actuate two modes and observe two modes of vibration instead of one mode, and then the same effect will happen, So it's a simple, this is an eigenvalue problem, simple without talking about complexity in thermodynamics, but from a simple eigenvalue problem, if you have two variables and two unknowns, then the variables would be the mass and the temperature, and the known quantities would be the natural frequency of the first mode and the natural frequency of the second mode. Then of course it's trivial to get both and solve even linearly what is the temperature and so on. So without annoying you with details, but for this experiment we excited the structure with half electrode to activate the anti-symmetric modes, otherwise you will not activate them. And then we were watching the first and second mode of vibrations. I have to add that the higher order modes usually they are more sensitive to mass, because the effective mass of the mode gets essentially smaller, so they become more sensitive, and hence you see for the second mode usually you have more frequency shift when I expose the structure to mass compared to the first mode. So this is another additional kind of advantage. So in this experiment, we put environmental test and we raised the temperature from this value to this value, and these are some characteristics for the resonance frequency of each mode, the first, the second, and their ratio as a function of concentration of water vapor. And in short, there is only one operating point that satisfies the intersection of the practical or measured lines with the water concentration and temperature, which is these. So we say now in one shot we can get the temperature and we can get the concentration. But this is in the linear sense. Now I can add the switch idea to all of this, and then I get a switch that is triggered by mass that can compensate for temperature or can do whatever you want to get out of it. So I guess this is the experiment in which we get the switch out of a multimodal excitation. So this is the first mode characteristic where you see the pull-in, and this is the third mode. And again, this is the point, and this is the experiment of exposing this beam to vapor, measuring the response before exposure. After exposure, you see the first mode will pull in, whereas the second mode, of course, the whole structure will pull in. But now I have accurate detection of mass or concentration. So I guess I bored you enough with that. And the bad news, there are more to come. So take a deep breath. And yeah, let's just look into, instead of gas sensing, into inertia sensing. Well, same concept. I'm going to use the same concept. Instead of exposing this beam to vapor, I'm going to make it exposed to an acceleration signal. And in applications like in earthquakes or in structural health monitoring, you really need an accelerometer or a sensor to sense that there is a change in the dynamic load. And instead of sensing as normal dynamic load, there is, significant, if it's in structural health monitoring or even in earthquake, there is significant dynamical signal. But that significant dynamical signal in the language of G is like 0.1 G or 0.05 G. So your sensor has to be very sensitive nevertheless. So the idea, if I can have this switch, then it can sense the presence of an earthquake, for example, and it can shut down gas pipelines or nuclear power plants or whatever. So these incidents, you need an action. You just don't need a sensor that tells you what's the acceleration. You need an automatic alarm system or action to do things. So this is the idea. So the proof of concept was based on this accelerometer. It's commercial. And this is the characteristics of the pull-in curve as we explained. And this is schematic. I'm not going to repeat it. The only thing I want to say that when this structure is subjected to an acceleration signal coming from shock or coming from earthquake, the structure, the microstructure will view this as a quasi-static signal. So it will see the plate deflected very slowly. And when it does this, then you increase the electrostatic force. When you increase the electrostatic force, then you are inducing softening effect. So this curve, before exposure to that acceleration signal, has to shift. And same principle, if I'm operating this resonator outside, then it will find itself inside the instability threshold. So this is the experimental realization. I think this is a numerical error, but this is the pulse that we exposed this accelerometer. It's like, I guess, 0.05 G. And this is the experiment showing stable operation and then pull in, and the simulation also showing stable oscillation and pull in. And again, this instability is what I claim to be a switching action that I can make use of. All right, I'm going to pause for 10 seconds to have some water and then continue the second part of the presentation, which is really about shallow arches. So everything I talked about is a single well problem. Now, the beauty of shallow arches is that they are double well potential. And hence, there is much more complexity in the dynamics. And they can come naturally, like in carbon nanotubes, or you can design your structure to be, curved. Now, when we talk shallow arches, we talk about something like these dimensions. The length would be from 300 to 600 micron. And the curvature of that arch is very small, really. It's like 3 micron, 2 micron. So maybe our naked eye cannot distinguish whether this is straight or curved. Nevertheless, what is of interest that this curvature is of order magnitude close to the thickness. And that is the magic. This is where all the dynamics will be different from a straight beam. So this is in short what we have. The arch you are looking at will vibrate in plane. So you are looking kind of at this side of that arch. The rest is inside the wall. And because of that, because of the motion in plane, so if this is the silicon chip, this is the motion, laser is not good to characterize the dynamics because there is no up and down. So I have to use high-speed camera, essentially. So this is the high-speed camera. It's a stereoscopic images. And it allows me to capture the dynamics in air. But the bad news, I can only do forward sweep. I can do backward sweep, but the students complaining that it's too lengthy and complicated. So, and hence, let's stick with that disadvantage that most of the time I will show you only forward sweep. So this is the model, and the model, if you start with the just Van Karman strains and accounting for initial curvature of W naught, then you get something like Euler-Bernoulli beam equation, but it has the quadratic nonlinearities and the cubic nonlinearities. And when we, of course, set W naught equal to 0, you restore the nonlinear Euler-Bernoulli beam equation. One way to model this is multi-mode Galerkin. You use 4 or 5 modes or 6 modes until you converge. And these are just classic results, nothing fancy. This is linear behavior. This is softening. Now the arch is different from the straight beam, that here the dominant nonlinearity geometrically is really the softening because of the quadratic nonlinearity. So you get softening unless you get a snap through and then it comes back into hardening. And I think this is local oscillation, and this is something like snap through motion showing that dynamics. Now you can look at complexity and see, you know, potential chaotic behavior and what have you. I'm not going to bore you with this. Now, there is a concept that I want to introduce in the arch. Something good about it that it's very tunable. You can tune the stiffness, linear stiffness of an arch. You know, the more curvature you have, the higher stiffness you get. And that simple concept is the reason why, you know, people in Rome and so on, they used arches for buildings, because they have higher stiffness. So then this means if I can actively change the curvature of the structure, then this means I can push it and realize higher curvature and get higher stiffness, linearly speaking. So, and then we found that we can do this easily without building any mechanism. Just pass a current through this structure. It's like a wire. Then from electrothermal heating, Joule's heating, you can heat the structure, and then you can get this ability to increase its stiffness as a function of the voltage load you apply. So this is nice because I have now an active way to control the stiffness of the structure. And for us in nonlinear dynamics, we know we can use this for many reasons. So one of them is internal resonance. So now you are looking at this structure, and you are looking at the first and third natural frequency. I mean the first two symmetric frequencies of that structure, and you see how they, you know, up and down. And when you look at the ratio, they lock in at sometimes at a ratio of 2. Very easy. And for another structure, the ratio can be 3. So these structures, they actually suffer practically from internal resonance. And it's believed that this mechanism is responsible for reducing their efficiency or lowering their quality factor and so on. So from a fundamental point of view, fundamental understanding, people are looking to reliable experimental and theoretical data into internal resonance. So this is our attempt. This is some experimental data showing the 2-to-1 internal resonance, linear response, and then progressing into kind of more classical 2 peaks response characterizing internal resonance 2-to-1. And this is what we believe evidences of half bifurcation and some instabilities, which unfortunately, because of the camera, we cannot get more concrete experimental data. But one way we thought, okay, this is in plane, but if I shine a laser, maybe I can get the frequency content of that signal. So that's what you see here. This is the fast Fourier spectrum for obtained based on laser data. And outside the resonance, you get a single peak. I don't know if you can see it. If you don't, you have to believe me. Then this is a single peak, and within the internal resonance, the emergence of 2 peaks indicative of participating of 2 modes, essentially, and after which one of the peak will dissipate and the other will be weak. So let's get analytical. And we apply the method of multiple scales. So essentially, we perturb around the static deflection, and then, you know, expand this in Taylor series, which is a restriction on perturbation. But, you know, I'm going to stick to some local dynamics here. And the question, where do I stop? I mean, I can stop at this level or at this level or at this level. It's really up to us, right? If you look carefully at this equation, what do you see? You see external forces, forcing term. You see parametric, higher order parametric, another higher order parametric. We can argue these are not important or important. We don't know. So I guess the approach is to compare with experiments, and then we will see how many terms are needed. And this is kind of a feature that sometimes, or I would say, no one I think is smart enough to figure it out before comparing to experiments. So with no shame, sometimes it's a trial and error. We just keep doing perturbation again until we fix and see good agreement with the experiment. The second remark I want to add that this V of t is not really a single source excitation, it's a two-source excitation. So, I mean, we can be lazy and neglect this term and be happy with more standard perturbation analysis, or we do what is right with maybe extra math and account for the two sources. So I'm going to talk about this. So here we do what we call direct attack for the partial differential equation, rather than doing Galerkin and doing perturbation for reasons of convergence. And without boring details, you do order epsilon, epsilon square, and epsilon cube. And as I said, maybe for people who likes perturbations, this forcing will show up balanced with damping and so on at this order, and you see this and this two direct excitations terms, and then the rest, the parametric, will show up in the third order. For example, at some point we stopped here and said we don't really need all of this. But again, you don't get a good match with experiments. All right, so this is the standard perturbation. You get modulation equations for the amplitude of the mth mode and the phase of the mth mode, same for the n. And, you know, in short, W would be composed of the response of the mth mode and the phase, and the nth mode and the phase, and some correction factors. All right, so here the numerical results. First of all, compared with Galerkin. And I have to say something here. It's very unusual to study internal resonance using Galerkin. And I think one reason, because with Galerkin, if I don't see this analytical curve, I cannot predict what is this. If someone gives me this, I will tell the student, this is junk. But now, because we know ahead of time that there is something here and there is a half bifurcation, we accept the results from Galerkin. So again, I want to emphasize that I don't think Galerkin will replace, and many of us know this, the analytical techniques of perturbations. Now we do this because we know. We just want to verify the convergence and stuff. This is comparison with experiments, and you see good qualitative, kind of also good quantitative agreement among the results as you sweep the excitation and make it higher. This is where I compare experiment and theory using two approaches. The approach where I get the two terms in my excitation and one term, you know, neglecting this term, which is kind of a habit in the literature. So anyway, it's clear that the two terms will give you better matching between theory and experiment. And I'm not sure what happened in this case, whether we started with this and then we corrected or what, but it's clear that, you know, comparing with experiment will tell you what you are supposed to do. And now if you increase more the excitations, you get to enjoy complexity in the dynamics, as these short videos show. And this is where, of course, you cannot rely on perturbations. You have to rely on some other techniques. And you see evidences of crazy behavior, you know, sometimes very high frequency, sometimes low, sometimes. These are short video clips. They are qualitative, so don't think too much about them. When I compare this with some lazy numerical simulations using Galerkin, then you see strange attractors, and you see quasi-periodic motions, and you see stuff that, you know, with some more energy, you can apply maybe more robust continuation techniques to study or flow K theory and what have you. All right, so finally, this is something new. We thought, well, we saw 2 and 3 to 1. How about 1 to 1? For that, you can excite the structure with half electrode, and then you can look at this mode, which is typically the anti-symmetric and the symmetric. They cross at some point, and we were interested to see what's the impact of this on the dynamics. This is preliminary data, incomplete, but this is what I got. So these are experimental data showing before crossing, this is the first mode, it's softening. The second mode is hardening. And at crossing, it seems they both at 1:1, they are locked into one longer version of frequency response curve. After crossing, we see this is doing funny things, which is hardening and then softening. So this is mixed behavior, and that would be this mode, the second mode. And the first mode is kind of going back to softening. And you know, I don't think this is a clear picture. We need some analytical work and perturbations, which is undergoing. But what I'm trying to say that in the literature, when I look at the classic literature, and I look for who did that, and usually people have done it 30 years ago or 20 years ago, especially NAIFA. You know. But I don't see results. I don't see qualitative results. If I just want to answer this question, would that be physically possible? Honestly, I don't see answers, even from a theoretical point of view. So I guess it seems to me in 80s and 90s, there were interest to solve problems rather than to show behavior, meaning the dirty work has been done already. And what I'm trying to see here is just more of a qualitative understanding and a picture to see. And this is common in many of the research that I do. I discover these problems are mostly classic, but not much in terms of force response curves and frequency response curves and stuff that we can compare in terms of experiment. For example, many times you see these responses as A1 and A2, amplitude of the first mode and third mode, but you don't see, you know, collective results. All right, I guess I have like 10 minutes for applications, so I'm gonna speak fast. So first, if you have a tunable resonator, this means you can build a bandpass filter, and that bandpass filter, you can tune it actively. The idea, you know, higher voltage, higher frequency. So I can really realize two identical resonators, one of this resonance frequency, the other. If I get them closer to each other and collect their electrical response, then I get a bandpass filter. And that bandpass filter, I can argue it's tunable because I can tune its resonance frequency using electrothermal voltage. So this is what you see here. The center frequency goes from like 130 or 120 kilohertz to 260. And these are the experimental realization. This is linear. Another filter idea is actually to get combining the nonlinear response of two resonators. So the idea here that if I can get this, you know, one of the resonators to do softening, the other ones to do hardening, and I bring their response closer to each other, then I can get these jumps to surround the band pass where, or this band where it's desirable to pass the signal. So this is called sharp roll-off from the stop band to the pass band. And this is not like a near ideal filter would be based on the jumps. So how do we do this? You can have a beam, and essentially what we did, one beam we lift it to work at the hardening behavior, the other beam identical, we buckle it, and then we worked at the post-buckling behavior like an arch to get the softening behavior. And this is the hardening, this is the softening, and this is the collective, you know, combined response showing almost ideal bandpass filter. All right, this is better than linear, but still I have two devices. Can I use one device? Yes, but I need to resort to another nonlinear phenomenon, which is veering or mode coupling. So in many of these devices, you get to see one mode getting very close to the other mode. For people who know mode coupling of veering, you know that at this regime, those modes will kind of get hybridized. So I guess this is animation showing the first mode becomes mix of this and this. Also the second mode after this veering becomes a mix. And this is well established in the literature. And this is theory and experiment based on eigenvalue problem and what have you. So the idea here, I want to make use of this veering, because veering is a mechanism for coupling. So it's like having two resonators, one at one mode and the other at the second mode, and then they are coupled linearly through veering. And one mode usually shows hardening behavior, the other one shows softening behavior, right? Or the opposite, softening, hardening. At veering, this is experimental data, you get to see those jumps merging, and then you can get a nice kind of a bandpass filter. Maybe not as flat as we want it, but it's a promising idea, I would say. All right, so I'm gonna keep throwing to you applications until my time is up, so bear with me. Another linear principle, but I will twist it non-linearly in a minute, that if you have this wire and you are heating it, then you can cool it. And when you cool it, and if it's an arch, cooling means change in the resonance frequency, less curvature, right? So I literally can have a pressure sensor where measuring the resonance frequency will be an indication for the amount of pressure I am having. And this is without big diaphragms, and we call it scalable because you can scale it as small as you want, etc. Okay, the fun part, I want to make use of this actually as not a pressure sensor, as a gas sensor. So this is kind of a new idea. And to tell you the truth, the idea came from my students, not even from me. They said, why don't we change the environment of the chamber, and instead of having air, let's get some other gases and see if we can use this for sensing. So what you are looking at here is a buckled beam. So the beam, before it's buckled at the first mode, the classic frequency response, the resonance frequency, and then this is at the buckling. It does not reach zero usually, exactly, but this is the depth of buckling, and then this is post-buckling. And then they were also watching the second mode of vibration. The second mode of vibration does this. And they were like, we would like to operate near this buckling instability where I have maximum sensitivity, and I want to expose this beam to two kinds of gases. First kind, where you have thermal conductivity of the gas higher than the air. Higher, so there will be more cooling. More cooling, if the beam is buckled, then it has to go backward, and it will be kind of in this regime. So I start to measure data along this line. But if the thermal conductivity is smaller, then less cooling, then you are probably gonna ride these curves. And this is recent experimental verification for this based on helium and methane. So these are, I guess, the more cooling case, seeing what these modes are doing. So you have the resonance frequency increases. And this is the beauty of the second mode. How do I know if I only measure this mode, whether the frequency increases in this direction or this direction? There is no way to tell. But if I'm measuring and observing two modes, then as you can see in this case, where I have thermal conductivity less, then the first mode was increasing and this was constant. So this is kind of selectivity. Now all of a sudden I have a selective gas sensor that is selective for the kind of gas depending on whether thermal conductivity is high or low. Of course, it's a premature idea and there are maybe lots of issues to worry about, but it's promising. All right. So I guess this is the final application before I give you the liberty of freedom. So this is electromechanical computing. It's a kind of intriguing, exotic application. So, 200 years ago, people were doing computing using steam, like this sketch of Babak. And of course, then transistors came and got those people out of business. So it's an irony now that I stand here after 200 years trying to convince you that we can do logic again using mechanical concepts. This is far away from reality, so don't get too excited. There are plenty of issues to worry about, but this is the promise. So let's put it in this context. The current CMOS transistors, they have issues. They reach physical limit in terms of energy saving and in terms of how much you can put into one physical space. So there people are seeking and searching for alternative logic units and alternative ways to do computation. And one of them is through MEMS. The idea that unlike transistors, MEMS, when they are in the open circuit, they don't leak energy. Whereas transistors, as many of us maybe know, that they leak energy, they leak current even in the off state. So there is a path maybe for energy conservation or energy consumption reduction. The problem with these research based on MEMS switches is that they rely on contact. And the previous presenter said a lot about contact. Contacts present lots of nonlinear effects and distinction and issues. So can we do logic, electromechanical logic, without contact? So actually, yes, and this is one of the first work in 2007 which proposed to use logic devices based on the state of the resonator, whether it has high amplitude or low amplitude. The high amplitude, if we can read it electrically, then this is I signal in the logic. And if it's off resonance and you have low signal, then this is 0 or O. So this is the basic concept. And they are non-contact, they are scalable, they are reconfigurable, meaning I can do lots of logics in the same unit, unlike the static units. So this is using electrothermal, same concept. Here I can build a circuit just controlling the amount of compression in that arch, right? And hence the amount of resonance frequency. So if this circuit is open at A and B, then if I look at the electrical resonance frequency of this structure, then this is what you get. If I close one of these switches, then there will be current, heat, arch, which means higher resonance frequency. So you will see shift like in the red or blue curve. And if I close both switches, I will see the magenta. Okay? So what's the idea of the logics? The idea of the logics is that you want to operate at a fixed frequency, say for example at the magenta, and then you read the output signal of your resonator. In this case, if I am operating here, then the output is 0, 0, 0. Unless I have A and B on, then I will read 1. And this is an AND gate. So it's really a trivial idea. So this is the AND gate realization. And this is the signal. You put, switch A on, switch B on, and then you see the high signal. If they are off, you see nothing. If one of them is off, I think you see nothing, and something like that. There is no time to go through details. And you can get all kinds of logics, XOR and NOR. Now, there is a trick of what I said, that the input was DC voltage. The output that I'm showing you here, this is kind of an AC voltage. So the trick that if I want to realize a realistic computer or computing unit, then I need the output and the input to be of the same form, so that I use the output of one unit, feed it as input to the other unit. Otherwise, how do I feed DC and output AC? Unless I need a converter, which is complicated. So how do we do about that? So I'm going to just demonstrate last idea in this presentation, which is using subharmonic excitations. So let's take a look at this simple system and just take a look at the equation where the electrostatic force shows up. The electrostatic force being quadratic will give you quadratic term here, and 2 times this, and then this square, which becomes cosine 2 omega t. So this is the electrostatic force. So the idea, if I want to operate on AC only, then I don't really need this, and I need this. But here you look, okay, if you want to operate on AC, then you are exciting the system at twice the natural frequency. But the output probably would, exciting the system at twice the natural frequency means no resonance, or means almost, very weak signal, unless I excite it at subharmonic. So let me explain the idea more. So here, what I would like to say, I'm going to rely into this component to achieve logic. So this is schematic showing that I'm proposing to use input logic VAC cosine omega t from certain unit, the other unit VAC cosine omega t. Then the electrostatic force comes and square this, converting it into cosine 2 omega t. These systems, they have quadratic nonlinearity, so they already can be excited at subharmonic resonance when you excite them at twice the frequency. And we know that when subharmonic resonance is activated, it does not answer with 2 omega. It answers with omega. So by virtue of subharmonic resonance, I got an input of omega and output of omega, and I only use VAC, and hence I can feed this as an input for the next unit. So using subharmonic resonance, in my point of view, is promising to do this kind of logics, and it's cascadable, and it's promising. So this is the experimental, again, these are proof of concepts, realization of this. And you see for this clamped beam or what have you, you see the response is 0 here when you don't have any VAC. 1, 0 or 0, 1, meaning one of the VAC input is exciting the system, and you see this response. And if 2 inputs are coming, then you see the subharmonic resonance larger than the red. And if I operate at this operating point, then you can see that 0, I get 0. 0, 1, or 1, 0, I get also 0, almost. But only when I get 1, 1 condition, I get to read this large response, and this fulfill an AND gate in terms of logic. And I guess this is the more clear schematic for the input and the output. All right. So we're reaching the conclusion of this presentation. In short, I was hoping to demonstrate that there is intriguing, honestly, nonlinear dynamics at the micro and nanoscale. And I wish more of this community to put their hand into it. There are some of us work on this, but we created a vacuum, and that vacuum is being filled from other disciplines, and where the achievement of people from the 60s and 50s and so on are being not acknowledged properly, I would say. And the second message, I think that it pays to understand these nonlinear phenomena, because I argue they are promising for some new ideas. Maybe 90% of the ideas that I mentioned will never see it in the market, but I hope that few of them will make it to the market. So it's worth investing. And this understanding usually calls for planned, well-planned models and experimental data. So unfortunately, in this field, you cannot just rely on theory without relating to experiments. If the experiment does not exist in your group or facility, at least take a look at the literature, because, as I said, there are practical issues that only show up when we compare to experiments. I would like to acknowledge the KAUST Fund. Some of this was from NSF, the older research. There are plenty of talented people who worked on this from my group, and sometimes I put their names, sometimes I forgot. Hopefully they will forgive me. And finally, I would like to acknowledge Professor Naifa, who I had the pleasure of inviting him to my campus recently. And actually, he visited me 3 times in KAUST. And this picture shows his enthusiasm when he was in my lab, and the energy I saw. I personally got sick watching experiments, and I told him, let's go have lunch, and he insisted he wants to wait. He waited for 3 hours for some experiment of vacuum and stuff like that. So of course I acknowledge him for everything I know in this lab. Thank you very much for your attention.